Hello, welcome to ZP here in Norway. Today we're going to be doing a live demo of how to test the nitrate sensors that ZP manufacture. So our nitrate sensors are based off an ion selective membrane and primarily used in agricultural applications. So here in front of me I have one of our nitrate rods. So this rod can be planted in a farmer's field and help to give them an idea of what's going on beneath the surface of the ground to help them accurately manage their fertilizer applications. So during our demo, we're going to be testing various solutions of nitrate solution on one of our Zimmer Peacock sensors, along with the PalmSens equipment. Thank you very much.
Yeah. Hi, I'm Lutz Stratmann with PalmSens, and I guess you already. Some of you, I guess, are returning people, some of you are new. So for those who miss now Martin Peacock from the company Zimmer and Peacock, don't worry, for the Q&A session he will be there. And as I said, I'm Lutz Stratmann from PalmSens, because this is the cooperational webinar that we have done now 3 previous editions of. You can watch on our YouTube channel the other episodes if you have missed them and if you like this one. Today we're going to talk about nitrate, and as we was just introduced by Matthew from Zimmer and Peacock, this is very important, for example, for agricultural applications. I will give you a short theory introduction, and then Solron will show you the live demonstration, so the real measurement. But first we would like to get to know you a bit better. We have a short poll for you, and we would just like to know what brought you here. Why do you find this webinar interesting? Yes, so it's just basically, just if you give us that feedback, we can see like why are you interested in our webinar, and maybe make future webinars that meet what you're interested in, right? Because we want to make it for you. Without an audience, this would be quite boring, especially the Q&A session. Right. Artie, will you give me a sign when we close the poll? Very good.
Yeah, I will give you a sign, and we already have a few answers going on, so that's nice.
Great. Oh, that would be a good opportunity as well to introduce Artie, who is again with us this time as your voice, because he's the one curating the chat. So he's reading what you're writing, maybe answering directly, or keep your question for the Q&A session. And then, yes, we will hear them in the Q&A session. That means you can write your questions already into the chat if that's what you want to do. You can also wait till the end to see if we have your question, if we already answered your question in the presentation. So today we want to talk about nitrate. Right, so the first question is then, what is nitrate? Well, you see here this rather simple molecule with a structural formula. And nitrates are the salts of nitric acid, which is HNO3. So it's usually NO3 minus that we're looking at when we're talking about nitrate compounds, and the nitrate ion is what we're actually interested in. So this ion has a lot of commercial applications. So you find it in explosives, for example, because it is a source of oxygen, right? You see there's oxygen and nitrogen in there. And the nitrogen molecule, so when you have N2, that's a very stable compound. So that's often very easily formed. And then you release oxygen, for example. You will also produce some other NOx compounds that are not very healthy, but it's a source of oxygen in these kind of explosives, or also to accelerate any type of, incineration. So it also can use it as a food preservative. So you use it to keep your food longer fresh. I think we have most likely heard about nitrates in food, especially in meat products. And it can be used as a fertilizer, or it is often used as a fertilizer, because it's a nitrogen source for the plants that they can digest and create their proteins from. Because as you know, if you grow plants on a field, then you take the fruits of these plants away, you've taken a bit of the proteins and the nutrition for the plant from the ground and brought it somewhere else. But then the next time you want to grow plants on the same field again, so you have to bring nutrition for the plants onto the field. And that's usually done with fertilizer or maybe manure, because it's, basically there's nitrates in there as well, or ammonia. Nitrate has no direct toxicity, which makes it nice, and this is why we use it in food products, for example. However, nitrate can form in nature nitrites and nitrosamines. Also sometimes in digestive processes this can happen as well. And these are toxic compounds that can block our breathing pathways. And that can lead to severe health problems as well, especially for newborns and babies. That can be a problem if you use water, if you use for a long time water that has a too high nitrate concentration. You can block a lot of their breathing pathways, and you're suffocating the child from within. And also, additionally, not only for our health, but also for nature, it's a danger, because if you have a lot of fertilizers in water, you increase plant growth. Well, why do we then put this much fertilizer into water? Why do we put nitrate into water? How does that happen? Well, the reason for that is that we need the intense agriculture, we need efficient agriculture. We're using the ground we have. We need ground to live on. We need ground where our food can grow on. So we need to put fertilizers on the ground so we can reuse our soil. However, it's not very easy to really control the right amount of fertilizer to put onto the ground, or the manure you're using. So often farmers use a lot to make sure that the ground has enough nitrate, that the crops are growing properly. But rain will wash this out and wash it into the groundwater. And what then happens is that the groundwater has a high nitrate concentration. And actually, we have 28% of the groundwater wells in Europe that are exceeding the recommended limit of nitrate in drinking water, which is 50 milligrams per liter. By the way, there is the number of the corresponding EU report if you want to look it up. Usually, nitrate is not removed by traditional water treatment. That means when we wash more nitrate into the groundwater, we will drink more nitrate in our drinking water. Also, more nitrate or more fertilizers in general in bodies of water can lead to eutrophisation and anoxia. These are complex words that just means a lot of plants are growing in the water, and these plants will use up the oxygen in the water. Latest, when they decay and bacteria start to decompose the dead plant material, a lot of oxygen is used up, and you will basically suffocate everything in this body of water. I think everybody knows some water where there's just the whole water is destroyed by the suffocation. So you know, some pond in a park or something. And to remind you, not only nature is in danger, but also it's a health risk for us. Things that can happen is you can have the blue baby syndrome, what I described before, that pathway in the baby's bodies are blocked. You can have anemia and breathlessness, or even you can fall into a coma if you constantly eat high nitrate concentrations. So it's not like, if you look at nitrate, it's not a super toxic compound. However, it can have an impact on your health if you have it basically in your environment the whole time. And this is not something we want. And Matthew has already shown you the this rot sensor system, and that is developed by Zimmer and Peacock. So they started with, let's say, a rather simple system. If you consider these type of electrodes, they're rather simple and look nice. And then Zimmer and Peacock developed that further into that soil probe that you can, install in the soil, and so a farmer can better monitor how much nitrate is actually in the ground, and maybe he can save fertilizer. So even an economic benefit for the farmer to use less nitrate, to use less fertilizers, be it manure or directly artificial fertilizer. Yes, so this is a good thing to do. And Matthew also already mentioned that this is an ion selective electrode that we are using. And I think this is also a great time to just have another poll with you guys, because ion selective electrodes are actually a broad field of electrodes. And we have a poll where we would like to know which ion selective electrodes have you guys used. Right, at the moment there are a few. There's definitely one that I think is the most used and most popular one, and I would expect that this will have the spike. But of course we're interested in other ones as well. The poll is launched, I guess. Yes,
yes,
great.
It is.
And Yes, so yeah, so if you you have different answer option. If you have used ion selective electrodes for interesting ions before and it's not in the list, just feel free to write that in the chat as well, that we learn something about this and can maybe can maybe use it for future developments, right? Okay, can I go on with the presentation while the poll is running?
Yeah, sure.
Okay, cool. So first of all, an ion selective electrode is usually an electrode where the potential of the electrode only depends on one ion, ideally, right? You know that the idea and how things work in real life are sometimes a bit different. You can make a barrier that blocks out most other ions, but there are often some interfering ions. Maybe they're very similar to the ions that you're looking at. Maybe they have a similar radius, etc. So it's not always easy to have like the perfect one ion membrane, but ideally it's only one ion that you let through. And I already said, yes, they're based on a membrane. So you just want to have the potential depend on one ion. And one way of doing it is taking your electrode and putting a barrier between your electrode and your measurement solution that will only let one ion through. So usually that's in this barrier, which is usually a membrane, so a thin layer. There's a ionophore in there that will transport ions through this layer, and you want it just to be specific ions in an ideal case for your electrode. Okay, so the most prominent example from my point of view for such an ion is the pH electrode. It doesn't use, well, it uses a glass membrane, and if you're very particular, you can look in detail in it, and the protons are not actually going through the glass membrane, but they have some interaction with it that's creating the potential drop. But we don't want to go too much in detail here right now, but that is a very prominent ion selective electrode, the pH electrode, and I guess a lot of people have already used that in their lab, for example, when they're making buffers and need to adjust the pH. Right, I would expect actually that this would have been the one that gets the most votes on the poll. Ardi, is that the case actually?
Well, actually it's the pH.
Yeah, it is the pH electrode. Yeah, that's nice. Yeah, that's what I was expecting from the poll, that the pH electrode would be the most popular or the most used one, because it's almost in every lab. Okay, the setup is actually quite simple for such an electrode as well, because you just need two electrodes. You need one safe behind the membrane and another one as a reference electrode inside the solution. Right, for the pH electrode, actually, now you might realize it's not one, but it's two electrodes. This is why, for example, the one you see here in the picture has a BNC cable, and that means it has a cable that has a core and a shield around it, and you can use both for connection. And the shield is then sitting on a different electrode, not just on ground, just on a different electrode, and the core is sitting on the other electrode for your setup. So you have one reference and one that is specifically giving a response for just one ion. All right, and you measure that response usually with a potentiometric measurement, and the measurement of choice is here the open circuit potential measurement. That means the potential that you measure when no current is flowing. Some people might also know it under the name open circuit voltage. All right, and now, the response we're measuring, we also want, of course, to relate to the concentration. So we want the potential change to correlate with the concentration change, and that we can do with the Nernst equation. And if you're interested in electrochemistry, and you are not a big fan of math, you still should carefully look and study two equations. And one of them is Faraday's law, and the other one is the Nernst equations. These are the two equations I think are really essential to everybody who's doing electrochemistry and understanding how they work. Okay, so in this case we have the Nernst equation already slightly simplified. We have the potential of the sample, or of the electrode, and that equals to usually the standard or reference potential. Often you use the formal potential for this, plus, and then you get like a coefficient that makes up out of a lot of constants. We have 2.3 as a conversion factor between the logarithm to the base of 10 and the Ln. We have the universal gas constant, we have the Faraday constant, and then N is basically the charge of the ion. Usually it refers to the transfer of electrons. That's different between the oxidized and reduced species, but for ions that is usually the charge of the ion. And the temperature in Kelvin. And the whole thing is multiplied by the logarithm of the activity of the ion you're interested. Well, often this is further simplified by assuming the activity constant is 1, or you include the activity constant in your reference potential. However, you do get then a logarithmic reply between concentration and potential. And you see, of course, that means you have to carefully choose your measuring range, and you should pay attention if there is a certain range on your ion selective electrode advised to use. Okay, well, now we have now learned the theory behind it, and we see, okay, it's not awfully complicated, it's all right. But then this measurement, isn't that complicated? Because it sounds like you need a lot of things, like you need 2 electrodes. Well, it's not that complicated. You need your sample, of course, and if you have a good compact system, you just need to have this one chip or one probe where you have your reference and your ion selective electrode integrated. And Zimmer and Peacock has, of course, such a small electrode that you can use for ion selective measurements. Maybe Matthew can tell you later more about the many different ions they actually offer, so for ion selective electrodes. But today we're looking at nitrate first. And you, of course, then need the electronics to measure your open circuit potential, and that is something you can do with the Sensit Smart, which is our very small potentiostat. You can see in comparison to the smartphone that it's a rather compact system, but it's also very versatile. You can't do only OCP measurements, but you can do more with it. And you need, well, in our case, a smartphone with the app PS Touch to control the whole thing. Right, and just to show you again or remind you why you see 2 companies in these webinars, one reason is PalmSens is here for the electronics, for the potentiostats, and we are just a good combination with Zimmer and Peacock, who have a very good grasp of the technology, of the chemistry and electrode design. So they're also very, as you have seen in previous slide, they're very good at bringing their technology from an electrode to an application, right? You've seen the soil probe. And talking about bringing stuff from a technology, from a proof of principle to a commercial product, well, we have the Sensit Smart, and the Sensit Smart is based on the Amstead Pico, which is our potentiostat module. And that means you can use the Amstead Pico also to build your own devices around it. It's a stem-sized potentiostat that you can integrate in your systems if you want, for example, to build a handheld reader. Maybe a handheld reader that has an autosampler integrated. I don't know what your imagination can come up with. If you want more information, just visit our website, because I don't want to keep Solron and Matthew a lot longer from their experiments. Just one more thing. If you want to help Zimmer and Peacock develop their nitrate sensors, they do have a beta tester program that you can join. There's information on the website. There's a link on the bottom of this slide that you can use to visit that website and learn something about the nitrate beta tester program. I don't know, maybe Matthew also wants to lose a few words about that, or Solron, but well, Solron and Matthew, the floor is yours.
All right, so yeah, I'm Solron, and this is Matthew. And as Lutz was saying, this is really simple due to the gear that we have. So what you need is a smartphone with the pre-installed PS Touch app. So we will access that, and we will insert the Sensit Smart, the small potentiostat, into the smartphone. Together with it, we will be using a nitrate sensor from Zimmer and Peacock, which is, as Lutz said, an ion selective membrane. So we will insert that into the potentiostat, and it's important to align the electrodes with the lines of the potentiostat so that the electrodes are connecting. And And I assume that you'll see my screen. Yeah. So for the method, we will change the settings. Well, we'll have a T run for 500 seconds. That's more than sufficient. So that's what we will run with. And now we will dispense some solution onto the sensor. And these solutions are 3 different concentrations of potassium nitrates. So we will start with the lowest concentration, which is 0.3 millimolar. And I prepared 60 microliters, which by experience is the perfect amount to cover the electrodes of the sensor. So I just pipette it onto the sensor like that, and then I hit play. And now you will see that a line is forming, and we'll just wait a little while. Yeah, here, and it's a flat line. And what we will do is that we'll prepare for the next solution to be dispensed onto the sensor, which is a higher concentration, 3 millimolar. We will remove the solution that's already there. We're doing this because it's more simple. You could also pause it and start it over just to get better data, but just for the smoothness of the webinar, we'll do it like this. So dry it off like that, and dispense the new solution like that. And here you see it went down. So it started forming a new line with a lower potential for the higher concentration, which is exactly what we expected. And if everything goes as planned, it will now, for the next concentration, which is 30 millimolar of potassium nitrate, we will see an even lower potential. So we'll again wipe off the solution and put on the next concentration like that. And here you see perfect steps for each concentration. So this is an open circuit potentiometry. So what it's doing is that it's measuring the potential between the reference electrode and the working electrode. So it's a really easy experiment, and it gives clear data, as you can see here. So I'll stop the experiment now.
I would almost say that you must be inventing that data. It's too perfect.
Well, you do see the small bump there when I'm wiping off the solution. So it could have been better if I paused it, but
yeah. It could have been yeah, no, but I mean, that's the scary thing, that when the data's so nice, but well, very, very nice demo in front, live demo with a sensor, with that Sensit Smart. So I think I'm always loving electrochemistry, because actually you can get good quality data, in a live situation on a smartphone. And I find it very hard to imagine other sciences where you can do it like that. So no, thank you very much, Solrun. And as you say, it tied up very nicely with with Lutz did the nice sort of talk about the Nernst equation. The Nernst equation has this kind of theoretical gradient of about 59 millivolts per log of nitrate, and you weren't a million miles off that. And because we're pragmatists at Zimmer Pigot, we never try to get 59 millivolts per pH or 59 millivolts per log of nitrate, but it was quite clearly a nice strong signal. So I'm super interested to hear, Lutz, if you've got questions regarding other ion selective electrodes we've had experience with. We'd be happy to talk about that, talk about this particular sensor, talk about the beta program, Ardi and Lutz, whatever questions are coming in, I think we're always happy to answer them.
Well, actually, I already have one by myself. I was quite impressed by the response time. I thought that such a membrane first needs some time of swelling, like when you put it into a liquid, that it would take some time till it receives, till it has its full state. So was this like, did you immerse it before in the measurements, or was it like pre-swollen or anything, or is it really that quick out of the box?
Yeah, because I mean, it's a good point actually, because I was having a conversation with somebody the other day about a sodium sensor, and the sodium sensor that we make also responds pretty quickly. And they were telling me about their response time, and it was like 60 minutes.
Yeah.
At which point I thought, well, I'm more likely to be dead from dehydration than anything.
Yeah.
So no, you're right. We're surprised by that, but you're correct. They do respond fast. We haven't pre-soaked it or done any kind of tomfoolery or jiggery like that. It's a good formulation and it responds fast. And you're right. It wouldn't matter so much in nitrates in soil applications. If you're a bit of a sluggish response, who kind of cares? Like, things don't change over seconds. They change over, tens of minutes, if not hours. But I would say if you were doing sweat analysis, then you would want that kind of response time, if you were looking for chloride or sodium. So yeah, thank you for commenting on it. And it was a bit of luck that got us there, but it works, so we stick with it.
All right, great. And we also got a few questions coming in. And the first question is, I think it's best for you, Soren and Matthew, is how would you prepare the sample for the measurement? So what is the pH or the buffer and etc.?
So this is actually just potassium nitrate in DI water. And yeah. So pretty easy. And we just use 3 different concentrations of the potassium nitrate.
And just out of interest, we do actually put a 100 millimolar chloride solution in the background as well, so that we don't just get a conductivity change. I just want to mention that as well.
Okay, great. That sounds doable.
I've got a question. How would you do it with a real world sample? Like if somebody wants to send in soil or send in maybe water from a pond, or they're worried about their drinking water, how would you deal with that? Like how would you prepare that real life sample?
Well, most of the time we're not preparing the sample at all. I mean, the mindset of Zimmer and Peacock is that we make these sensors, we stick them in the soil, and we measure the nitrate in the soil. Now, what we're doing is we're often measuring the analyte of interest on a third-party device. So essentially, we have the truth and we have what the sensor's saying. So we don't try to calibrate on lab solutions. I know your question is slightly different, but people try to sometimes calibrate on buffers and then apply that calibration factor onto real-world samples. We actually end up calibrating on real-world samples so that when you then send in your real-world sample with its unknown concentration, we'll get a voltage, but I won't look at that voltage versus data from buffer solutions. I will look at the voltage. Let's say you sent me in pond water. We'll have a calibration factor based on spiked pond water samples so that we take out the matrix effect. So I think something that happens a lot in academia is people are making standard solutions in buffers and getting calibration factors. That's fine. If you want to make a sodium sensor for blood, then calibrate in blood. If you want to make a sodium sensor for saliva, calibrate in saliva. And so with your one, when it's not all of our calibration will work if the sample matrix is very different from what we calibrated on. But if it's going to be very different, then we'll end up calibrating in a sample matrix that's representative. So for example, for soil, we don't calibrate in liquid, we actually calibrate in soil. So then we don't have our matrix effect. So there's a bit of a secret for everyone there, but that's how you deal with unusual matrices. You calibrate in them.
Right. Is that like the standard addition method that you usually, or that is known from analytical chemistry?
Yeah, I think it is akin to, it is essentially that. It's easy, as we both know, there's a bit of a flaw in that argument. It's easy to add, it's hard to subtract. So if you're trying to kind of, when you're doing calibration, you need to kind of calibrate, let's say it was sodium in blood. Well, it's hard to say what the sodium in that blood was. So I can see that there's a flaw in what I was just saying, but we do try to do, as you say, a standard addition type calibration, or even sometimes just diluting it a little bit just to reduce the sodium concentration, for example. But we do try to calibrate in the sample, not in buffer solutions.
Right.
Great. Martin, what if people are interested in your nitrate sensors? How can they reach you? Oh.
Yeah, I'm just trying to think about it myself. All right, I'll give the real answer. Okay, we do have a contact us page on the website. So we've got a complicated website, but one of them is called zimmerpeacock.tech.com and then /contacts. That's a good one to reach us on. I think zimmerpeacocktech.com/contact us. That's a good one to reach us on. Everything great. Comes into that.
Yeah, and also on the end of this webinar, for everyone who's watching, you will end as well with a nice link, so you can see both the Sensit Smart as a link and also the nitrate sensors. All right, great. One question about making the measurements, and you touched it already. Can you make measurements directly on the soil, or should you put it in a solution with water?
No, so we do it directly in the soil. So we haven't gone into this today too much, but we've had these nitrate sensors in the soil for over 3 months at this point for continuous monitoring. So the whole raison d'etre of Zimmer Peacock, as Lutz said, is to get things into the real world. So we've turned these, I say we, Matthew has been part of the team of turning these nitrate sensors into real sensors. We're burying them into the soil at depths of 30 and 60 centimeters, and they've been in there for 3 months, just continuously monitoring. My philosophy is the less sample preparation you can do, the better. And people are always amazed. That's why electrochemistry is so powerful, because the sample can be really dirty, like soil, and you can still get a signal out of it. Whereas if it was optical, I think you would struggle a bit more because the sample's not transparent. So quick answer is we just is a strong word, put the sensors in the soil, and as long as the soil is somewhat damp, there's enough liquid to make contact with the sensor, and then we get a reading. If the soil is 100% dry, we won't get a signal. But then again, you don't have a nitrate problem, you have an arid soil problem.
Yeah, true. And Martin or Matthew, could you also explain a bit more what is the detection limit?
Yeah, so I'd say, Matthew, to tell the guys what we generally test down to, and then, because go on.
Yeah, so the lower limit that we generally test up to is about 0.1 millimolar. Upper limit is not quite as well tested, but it's up to 1 molar has been tested in the lab. So that's kind of the range that we've lab tested, and in the field you'll often see, obviously, I think it's much lower towards the about 0.4 millimolar in the field, I believe. But those are the kind of ranges that we tend to test.
All right, thanks. And does Zimmer Peacock offer any option for integrating their ion selective electrodes into microfluidic environments?
Yeah, we do. We do have what we call we have a kit for allowing people to do sweat analysis. Now that's not so interesting to nitrate, but we did, so some people are buying a sweat kit from us so they can put sodium type sensors for sweat analysis. So that's one example. We have something called capillary fill, which is another type of kit. So the quick, and we also have, so the quick answer is, especially on academics, we will support academics in integrating our technology into microfluidics. We're quite keen on supporting undergraduate projects and master's projects, and if people then want sort of a lot of support from us, in terms of PhDs and stuff, we would like to be their academic, their industrial supervisor. So yes, we will help people, especially in the academic community, but we would like to be quite involved in the project.
All right. And Lutz, I've also got a question for you. It's a more generic question about how would you, are there any resources on how to get started with making your own device, either on the PalmSens website or the Zimmer Peacock website?
So if we talk about, electrochemical device, so really the electronics, the potentiostat, PalmSens supplies actually, as I mentioned, for the Sensit Smart, also OEM potentiostats. That means you would buy a module that does all the electrochemical techniques for you. You just have to send the right code to it. and then it will perform the measurement, and you can connect all the hardware around it. You have access then, for example, also to the auxiliary ports that would allow you to send or receive triggers, or also connect something like a temperature sensor or a force sensor or these kind of things. And we do have the MStat Pico. We have a lot of information on our website as well. If you visit palmsens.com, you can see at the top like 3 tabs. One says research, one says OEM, one says corrosion. And if you want to build your own devices, you would need to go to the tab that's called OEM, and there's a lot of information there on like software development kits, for example, to write your own software for our modules. Also information on our modules. And I can imagine that people who are used to like high volume commercial applications, they say like, well, your potentiostat modules are a lot cheaper than, or are a lot more economical and to be used actual in our production processes. However, they're still in a higher price class than we would expect for a product where we want to make 20,000 pieces per month. We also have solutions for that. We've recently released a version of the chip, on the microchip, that the MStat Pico is based on with our firmware on. That means you would work on a chip level with a chip that is already pre-programmed with all the electrochemical techniques. So it still means you need to be a bit more of a hardware developer than with our potentiostat module, because you work then on the chip level. However, that enables you to have for a price that's more reasonable for large-scale production components, you would have there a complete solution, a complete module solution. We call it the MStat Pico Core, because it is the chip where the MStat Pico is based on. Right. That I think is how you can get started. To go to our website. Also, well, on our YouTube channel, we have a few videos on our OEM products as well, like the MStat Pico development kit. But on this OEM section of our website, you can already find like a lot of information. Yeah. And don't be too worried about programming. We support a lot of programming, so if you have a programmer with some basic skills, I'm pretty sure we can find a way how he can program on his favorite programming platform something for this device.
All right, yeah, thank you, Liz, for explaining how to continue with the hardware development. And this is now, let's get back to Matthew. It's about the sensor we used. And it's a question about the reference electrode. Matthew, could you explain what material the reference electrode is made?
So the reference electrode is Martin, I'll correct me if I'm wrong, I'm sure. It's a silver chloride reference electrode. And petal on top of that is a cocktail that obviously helps the detection of nitrate.
All right.
Yeah, that's correct. That's correct. So there is some commercial secret sauce on top of it, but it's more of a it's not an exposed silver chloride reference. It's more of a protected silver chloride reference.
All right, great. This is a question that is more difficult for me, but I hope you guys know it. So someone is using usually an ISA / T-sub on ion measurement. And is it the same procedure on this Simran Peacock sensor that we use? I hope you understand this question.
Just trying to understand it. ISA, it rings a bell with me. I'll might have to Google what ISA means, to be honest with you. So I don't think I quite understand the question. Is the
right? Or maybe
I just Googled it. I've just Googled it. It says individual savings account. So I don't think that's what they're referring to.
Yeah, I'll ask for clarification. No worries. Let's go to the next question. Yeah, what are the intra and inter-assay CVs and spike recovery results? Can we share anything about it?
I think this is. I think the spike recovery assay. I think this is what it's a bit what Lutz was mentioning earlier on, where you have an unknown sample. You might make a measurement on it, and then you might spike it, and then you look at the change in the signal. And that will kind of help you calibrate what the unknown sample was. So I think we sort of understand it. I don't think we have, I think I sort of 80% understand the question. I'm not sure that we have much more to add to it. I mean, it's a fine technique. It will give you a more accurate, let's say, result. So if the question is, if you're measuring something that's unknown, like a nitrate solution, and you get the nitrate voltage, and then you add in an unknown amount of nitrate, the step size, you can then use the step change as a way of back calculating what the original concentration is. I think it's a perfectly good technique. And if people want to make a very accurate measurement, then I would, applaud them for doing that.
Martin, I have a question for this. Like, when you order the ion selective electrodes from Zimmer and Peacock, do you get then the information for a calibration curve, or the procedure how to do your own calibration curve? Like how, what is the step there to basically get immediately started with the ion selective electrode?
Yeah, so we actually sell some calibration solutions. So with ion selective electrodes in general, I always find that the sensitivity is quite well conserved. It's the offset that is the variable. And even with the same electrode, if you take the same electrode and measure it several times, the offset's going to be up and down, up and down. I think it's actually quite sensitive. So the quick answer is, if people want to quickly get going with our nitrate sensors, you can buy the nitrate sensors and some calibration solutions. But it's not like, you have to be quite involved with these sensors. I mean, it's, the PalmSens, the Sensit Smart rather, is a very nice instrument, but you have to do a little bit of, tinkering with it to make it work well. And it's the same with our sensors as well. So we sell calibration solutions with them so that people can get going quickly.
All right. Martin, we got some help from one of our viewers. Thank you for that. About what does the abbreviation mean. So ISA is actually ion strength adjust. And the TISAB is actually total ionic strength adjust buffer. So then the question would be, what if you're using this ion strength adjust and also this total ionic strength adjust buffer on ion measurements? If you could use the same procedure on the Zimmer and Peacock sensors.
I must admit, I can see where the question's coming from. That's why I made a point of making sure that you knew when we were doing our calibration, we were doing it in a background of 100 millimolar chloride, so that you understood that, that we were trying to sort of smother the ionic strength changes. Mm-hmm. So that's why I made a point of that. Now, I must admit, we haven't tried those ionic strength buffers. I think it's an intriguing question, to be honest with you. That's why it's quite nice to do webinars, because it does give you, if you're looking for a more intelligent view on your own product, just ask the world. And I think it's one of those kind of questions where, there's something there we need to dig into a bit deeper, but we haven't. But I can see the value in doing it.
All right. And this is a good question for Matthew, or maybe also Søren. And it's a question we get a lot during these webinars. How many measurements can this sensor, so in this case the nitrate sensor, perform without a loss of sensitivity?
Without a loss of sensitivity? Well, we've had sensors in the fields, in soil for about 8 or 9 months, I think, and we still saw good sensitivity between the readings. So, we've not really tested it beyond there at the moment, but that gives you a good idea that they're certainly durable, certainly last, and you can get good results over a long period of time.
All right, that sounds good. And another question I'll answer myself actually. Lots of people are asking, like, can we get a recording of the video? And yes, you can. So we will send a recording of this webinar to everyone. We'll first edit it to make sure it's perfect, and then we'll send it out via an email, and you get a link. So no worries about that.
Can I ask a question, Artie? How many people do you think were online at one point?
Around 50.
Yeah, it feels like it. It's a lot of questions.
Yeah, there are many questions. There are more coming. So let's say we do a few more minutes of questions, and then we.
But in the spirit of the last question, I want to mention again, you can find on PalmSens YouTube channel, you can find the 3 previous episodes of this cooperational webinar. I think also it's on the ZNP YouTube channel, and ZNP also has a lot of other webinars. But yeah, so you can find on our YouTube channel the previous webinars as well, in case you found this very interesting and think like, oh, I should have watched the previous one and I've missed it.
And we'll send a link as well, so no worries. We'll send a link to the old ones. All right, just one more question to finish this webinar. How to keep the electrodes between measurements? That's maybe a thing for you, Martin.
These ones, I mean, we might do a little rinse down with distilled water, just to get the ions off them, and then sort of, maybe use a bit of tissue just to kind of wick off the solution. But then no special care. I mean, these things are left in the soil, as Matthew says, for 8 to 9 months. So don't scratch them, don't take them to high temperature, don't leave them out in the sunlight. But they're not super wimpy sensors. I mean, if they were immunosensors or enzyme sensors, we'd be having a slightly different conversation, but they're essentially a polymer sensor. So I think these are fairly robust. Rinse them down, dry them with with a bit of tissue paper, put them in the drawer so they're not in direct sunlight. And, as Matthew says, they've had a continuous operation for 8 to 9 months. So they're not the wimpiest sensor there ever was.
That's true, yeah. Well, there is actually, we'll do one more question, just because he already asked it earlier. Are there any interferences for this nitrate sensor, such as protons or any other anions?
We found a little sensitivity towards chlorides, but this is the thing about pragmatic biosensor development. I can understand a sensitivity towards chloride could be more important in some applications than other applications. So we found a little bit of sensitivity towards chloride, but at the kind of chloride concentrations it takes to interfere with us, you've got a chloride problem. You haven't got a nitrate problem. So it's the same thing again. That you can always find a problem, but then you've got to ask, is that problem real in the context of what I'm trying to do? So we have gone around looking for the obvious interferences, but not in the matrix that we're particularly focused in on at the moment, which is the soil.
All right. Yeah. Great, then we'll have to end this webinar. I would like to thank everyone for joining. If you still have more questions, I know we haven't answered all the questions because there were many questions. If you still have other questions you would like to have an answer of, just contact us via our webpage, either on zimmerandpeacock.com, so zp.com, or palmsens.com, and we can help you with that. All right, thank you all.
Thank you.
Bye-bye.
Bye.
Bye-bye. Thank you.